Okay, welcome back everyone. Let's get started from where we left in the last class. So just for a quick recap, we are performing stability analysis of, something to what we call it as nearly parallel flows, which were inviscid in nature. So if we just give a quick recap of the physical picture. So what we had is we had a base flow, which was a function of z. Okay, and remember we call all the start variables as dimensional variables. And when a base flow, for instance, the base velocity is varying something like this, and the base pressure, which eventually we found out that it is constant. Our objective was that if there are certain perturbations to this base flow or to the base properties, then we are basically trying to see how these perturbations behave, or in principle what we are trying to find is, will the perturbations grow with time or will the perturbations decay with time, is something that we have tried, that we have asked in this problem. So this is something that we call as the stability analysis of an inviscid parallel flow, and the objective is to get a expression which is a simplified version of the one that you derived in the lecture series, which you call it as the Sommerfeld equation. So what we'll do is we'll see the special case of Sommerfeld equation when the fluid is inviscid. This is something that we will try to figure out the ultimate expression, but the objective and the overall methodology remains the same as you guys have seen in the last class, and just giving you a quick heads up of what we did. So these are the notations that we followed. For example, we told that the total variable is denoted by a small case letter, and of course I say that if I have a star, it's dimensional, and the base variables were denoted as capital letter, and the perturbations were denoted by the small case letter with a dash in it. Okay, and we looked into something which is known as the linear stability analysis, whose definition mandates that the if I have perturbations, the magnitude of the perturbation should be less than the magnitude of the base flow. Okay, this is what defines linear stability analysis. And the consequence of the linear stability analysis, if you remember, what we did is we neglected all the non-linear terms that involves the perturbations as the variables. Okay, for example, we will see that very shortly what we meant by it. But as a start, what we did is we started off by writing the equations for the total variable, which are dimensional in nature, and then we what we saw is that the base variable trivially satisfied the continuity as well as the Euler's equation, which means that now this enables us to follow a non-dimensional approach to derive the governing equation of the total variable which we had. And we know that the base variable in dimensional and non-dimensional form satisfies the governing equation trivially. Okay, which means so the next task that we need to carry out is that we now need to derive linearized equation for the perturbations. Okay, so here what we did is we already know the governing equations that satisfy the total variables, which we know that the governing equations that the base variable satisfies are trivially satisfied, which means that if I subtract them from the governing equations of the total variable, in principle I should get the governing equations for the perturbations. And that's exactly what we did. For example, we saw that the perturb variable v prime, this is a vector, I forgot to write the dash, this is a vector, and it satisfies, and this is the continuity equation that the perturb variable satisfies. And similarly, we wrote the Euler's equation, and then what we did is we neglected, so in the regime of linear stability analysis, we neglected the non-linear terms in the perturbations. For example, terms like v prime dot gradient of v prime, it's a non-linear term, right? And since we call that the magnitude of the perturbations are less than the magnitude of the base flow, then in that context, or in that paradigm, we can neglect the nonlinear terms that are present in the equations, for instance in this Euler equation. Okay, and that's what we have written here. And finally we derive an expression for the perturbations which is linear in nature, and you can basically figure it out from this equation. Okay, so we had in principle four equations: one, the continuity, and the three equations from these vector equations which involves the perturbed variable v prime. Okay, and then the perturbed variable v prime can be written as u prime, v prime, and w prime, and these are the components of the perturbed velocity field v prime. Okay, and it is important to realize that this perturbed velocity, as well as its components in the x, y, and z axis, they depends on x, y, and z, and also t, because we precisely don't know what is the form of the perturbations, or what is the nature of the perturbations. Okay, this is something that we are actually going to calculate. So in principle, we are just going to calculate u prime, v prime, and w prime. So, and in general, even, and this is very important, even the base flow is even if the base flow is just dependent on z, and the base pressure is just constant, but the perturbations to it, they will depend on all the independent variables. For instance, x, y, and z if it's a 3D problem, and time t. Okay, and then what we did is we also derived the component wise form of this equation, of the Euler's equation, and the continuity equation, which govern the perturbations. And the component wise forms look something like this. You can see that indeed the component wise forms are also linear, where this capital U of z is nothing but the base flow, and all the dash variables denotes the perturbations. Okay, all right. Then thereafter, we looked into a very, very important aspect of this stability analysis, which is known as normal mode analysis. Okay, so the normal mode analysis says that I can write my perturbations as a function, which we call it as the eigenfunction, times an exponential of this quantity. And the idea of it, I have already conveyed in the last class, that this basically comes from the Fourier transform. That's it. Okay, so the idea of this is that if I have an unbounded domain, let's say in the x, I can always write, because I know that my perturbations are going to exponentially decay or grow with time, I can write my perturbations u prime as some functions of x times e power sigma t. And then this u hat of x, what I can do is I can write a Fourier transform, to be precise, where I will say that this u hat of x, it contains some coefficients which are ak sine kx plus bk sine bk cos kx. And since the domain is unbounded, okay, since the domain is unbounded, I need to I precisely so in fact I have all the wave numbers that is present. So in principle, I need to integrate this over all the wave numbers, and this is something that we have understood in details in the last class, and I believe you have understood why we have used a Fourier transform here and not a Fourier series. Okay, in fact, all there actually, I actually said, I made a little mistake by the words that I have said. In fact, this writing the perturbation in terms of this is actually an inverse Fourier transform, and not a Fourier transform, because I hope you can understand that we are constructing the perturbations in x space from the wave number space, as you can see. Okay, so we are constructing the perturbations from a wave number space to an x space. So this is actually inverse Fourier transform and not Fourier transform. So precisely, writing the normal modes, and constructing the perturbations from the normal modes, to be precise, is inverse Fourier transform. Okay, and then what we saw is that we can precisely, we basically took a prototypical 1D example and saw that you can always construct a perturbation using, let's say, so using a variable which is ck times e power sigma t plus ikx, where these ck's are functions of the wave number k. Okay, and we saw that this sigma, this is known as the eigenvalue. That is something that we have saw. And this u tilde or u hat of x, whatever we have represented, that's known as the eigenfunction. Okay, so this is the so this example, this prototypical example of using Fourier transform into writing the perturbations, we saw this for a 1D case, and this is something that we have generalized for a 3D case, where you represent, you have not represent. So basically what we have done is we have represented the perturb variable, which in principle were functions of x, y, and z, using this normal mode analysis from taking motivation of the 1D problem, prototypical 1D problem, I should say, which we looked in the previous class. Okay, so then what we said is, as a final task, what we said is that this sigma that we write, this is known as our eigenvalue, and we do a very little, we do a very nice, a very, what to say, I don't know, but whatever you do, whatever you say, we do a variable transformation, which is very easy, where we say that the sigma, the actual eigenvalue, we write this, we transform this into another eigenvalue, which is c, and the c and sigma are related as follows, that sigma is equal to minus I alpha times c. Okay, and we say that the wave number k, we represent it as alpha, and the wave number L, that is the wave number in the y direction, we represent it as beta. And then we argued that for instabilities, these parts, this is something that governs the instability, governs whether the perturbations grow or decay with time. And the condition for instability is that this factor I alpha times ci, this has to be greater than 0, and that's obvious because then only this term will increase exponentially, or which means that the perturbations will grow exponentially. Okay. The condition for this is that alpha times ci is greater than 0, and we know that wave numbers cannot be negative, which means that ci has to be greater than 0. Okay, that is the imaginary part of the eigenvalue c. And in fact, the sign of the imaginary part of the eigenvalue is what dictates that whether the perturbations will grow with time or the perturbations will decay with time. Okay. Similarly, for stability or for the perturbations to decay with time, we saw that ci has to be less than 0. Okay. Okay, all right. So that's what we did in the last class, and we will carry out the subsequent analysis from this point on. So what now we will do is so what we did, we basically wrote the perturbations as normal modes, and then argued that you actually don't need to do the integration over the wave numbers, because each and every modes behave independently. So it suffices just to consider one mode in your normal, it just suffices to consider one generic mode in your normal mode analysis. Okay. So the next task, so that maybe I don't know what step is this. Maybe I shall see from here. Okay. Okay, so I didn't write any steps, I believe. Or did I? Okay, I think I wrote at step 3. I don't know. Okay, maybe I'll write it at step 4. So the step 4 is, I hope you can now realize that what did we do? We had the governing equations for the perturbations, the linearized governing equations. We know that the perturbations can be expressed in terms of, normal modes. So the next step is substituting, So the next step is substitute the normal modes in the linearized governing equation for disturbances or perturbations. Okay. So we derived the governing equations for the perturbations. What we'll now do is we'll substitute the normal modes into the governing equations. Okay. So I will not. So basically, I hope you understand that what we'll do is I'll just substitute these things, this v prime, u prime, p prime, and also the u prime, which is the x direction velocity of the perturbations, into the governing equations, which are basically this. So maybe I'll write or rename this thing. So okay, this is 8a, and this is 8b, 8c, and 8d. Okay, so what I'll do is I'll just take 8a, 8b, 8c, and 8d, which are representation in normal modes, and substitute them in equation 7a to d. Okay, 7a, 7b, 7c, and 7d. That's it. So we'll just replace the u prime, v prime, w prime, and p prime in terms of their normal modes. Basically, that's all that we do. And this substitution I will not do at my end. This is just algebra, and I'll just give you the final answer, and you can check this at your end in your free time. Okay. So the continuity equation, which was something like this. If you remember, the continuity equation was del u prime by del x plus del v prime by del y plus del w prime by del z. This was, your continuity equation. And then if we substitute the normal modes, for example, we know that u prime is basically equal to u hat of z e power, sigma t. And then we have to replace sigma. Okay, let's write it as e power minus I alpha ct. Okay, because sigma was equal to minus I alpha c. That's what we use. And then plus alpha x plus beta y. Because I have, kx plus ly. So I'll write it as alpha x plus beta y. Okay, so this was my u prime. Okay, and similarly, v prime would basically be equal to v hat of z times this quantity again, e power minus alpha ct plus alpha x plus beta y. Okay, and w prime is equal to w hat of z e power minus alpha ct plus alpha x plus beta y, and what we'll do is we'll just substitute these normal modes, and similarly also remember there was pressure. So pressure was also p hat of z e power minus I alpha t plus alpha x plus beta y. Okay, and what we'll do is we'll just substitute these normal modes. Okay, so the continuity equation then looks something like this. So if you substitute this, just need to substitute this. So I hope you understand that if u prime is this, if u prime is this, then what is del u prime by del x? So del u prime by del x would simply be equal to alpha. Okay, sorry, it would be I alpha, I guess. 1 second. Let's see. Okay, so okay, hold on. I think I missed I somewhere. Yes, you should. Yeah. So see, this is ikx, right? Sigma t plus ikx. So here there would be an I. That's what I was thinking. So there, it would be an I. There would be an I here, and there would be an I here. Okay, there would be an I, and there would be an I. Okay. Okay, then I hope you understand that del u prime by del x, this del u prime by del x would be what? It would be just I alpha times u hat of z, okay, e power minus I alpha ct plus I alpha x plus I beta y, okay. Similarly, you can also calculate what is del v prime by del y. This will exactly be equal to I beta v hat of z e power minus I alpha ct plus I alpha x plus I beta y. Okay, and similarly, del w prime by del z would just become, see, this term is not a function of z, which means that this would just become d of u hat by dz times e power minus I alpha ct plus I alpha x plus I beta y. Okay, and then if you just substitute this, if you just substitute these terms into this equation, which is the continuity equation, it will look something like this. Okay, if you just do the substitution, you will see that this will just end up being like I times u hat of z alpha plus I beta v hat of z. Okay, I think there would be a beta. Okay, plus d of w hat, which is a function of z only, by dz equal to 0, because the exponential term would be common from all the terms, and it itself cannot be 0, which means that you can cancel the exponential term, and this term would basically imply that it is 0. Okay, so that's this. So this is the continuity equation upon substituting the normal modes. Okay, so this is the continuity equation upon substituting the normal modes. Maybe I will write down this equation as, let's say, 9a. Okay. All right. Similarly, if you do the same substitution for the x momentum equation, which is the x direction, which is the Euler's equation written for the perturbations in the regime of linear stability analysis, and if we take the x direction component of the Euler equation, it will basically look something like this. Okay, you just need to just do the substitution as we did for the continuity into the x momentum equation that we just derived. Okay, so it is I alpha. So it basically turns out to be I alpha u minus c u hat of z plus w hat times du by dz, okay, equal to minus I alpha p hat of z. That's your x momentum. Okay, maybe I name it as 9b, and your y momentum would look like I alpha times u minus c v hat of z, okay, equal to I beta p hat of z, okay, maybe that is 9c, and your z momentum equation is I alpha u minus c w hat of z equal to minus dp hat by dz. Okay, and maybe I'll name this as 9d. So I hope you understand what we basically did here. All we did is we just considered these normal modes and substituted it into these equations. That's all that we did. Okay, substituted it into these equations. The x momentum, the y momentum, the z momentum, and the continuity. I showed you the algebra for the continuity. Similar algebra follows for the x, y, and z momentum, and I believe you can do that substitution at your end. Okay. All right. Okay. So I hope you realize that what are actually the unknowns in these equations, okay? Because we saw that when we derive equations for the perturbations, we saw that u prime, v prime, w prime, and p prime, basically. These were the unknowns. And then we represented the perturbations, such that it has one function, let's say u hat of z times e power sigma t plus, let's say, ikx. And after that, we did some certain sort of transformation. So then, in principle, the unknowns are, see, the unknowns are these u hats, this v hat, and w hat, and also, this alpha, that is the wave number, because we don't know. So this wave number is not known to us, right? So we don't know what is, what basically is the precise value of alpha. I hope you can understand. So in addition to these wave numbers, for example, is alpha, beta, or I should say the other way around. In addition to these, you know, these the w hat, let's say v hat of z, u hat of z, these wave numbers are also unknown to us. The only thing that is known to us is, this base flow, that is capital U. This is something that we know a priori. Apart from this, in this equation, you know, I mean, these in addition to the variables, the hat quantities, the wave numbers are also unknown to us. So this actually makes it very challenging to solve for the unknowns here. And so what we'll do is, see, we in principle need to calculate, the wave numbers and the corresponding, so these are known as eigenfunctions, the hat quantities. In principle, we also require to calculate the corresponding eigenfunctions. Now the challenge is, see, we have four variables, and okay, I have four equations, okay, but alpha and betas are itself unknown to us, okay. So what we'll do is, in order to simplify our analysis, rather than solving for all the four, unknowns, which involves three velocity components, we'll use a small trick, and that trick is basically a theorem, and it's a very, very powerful theorem in hydrodynamic stability. And this is known as, so this theorem is, I believe you have heard this when we are deriving the Orr-Sommerfeld equation. This theorem is known as Square's theorem. Okay, so by Square's theorem, I'll formally write down, the definition. The Square's theorem said is that, so the output of the Square's theorem is that you can, in principle, consider a 2D system of perturbations instead of considering a 3D systems for perturbations, okay? Which means I can get rid of at least one component of velocity, and then I just have two components of velocity. And remember, if my problem is 2D, I can use the stream function approach. Which means, instead of calculating, the velocities and pressure, I can just calculate the stream function, and because I'm only interested in the perturbations, if I somehow can express the perturbed stream function, okay, in normal modes as well, and calculating that just suffices to solve the entire, problem basically. And that's the reason why we try to, convert the 3D problem into a 2D problem, such that we can take help from the stream function approach. And for doing that conversion, this is not an ad hoc, conversion that we do, that okay, so basically you just can't, naively convert, a 3D problem into a 2D problem. For that to be valid, it should satisfy this Square's theorem, okay. And Square's theorem, in principle, it says that 2D disturbances having the same wave number, and this is very important, okay, 2D disturbances having the same wave number are much, much stronger than, 3D disturbances. हेलो. हाँ. हाँ हाँ, कैंपस में हूँ, हाँ. हाँ हाँ, ठीक है, आ जाऊंगा मैं 6:30 बजे. साढ़े कौन कितने दो टाइम में है? हाँ. हाँ. 6:30, 1 घंटा के बाद है. अच्छा अच्छा अच्छा, ओके, ठीक है. मैं ठीक है, मैं वो वाले में आ जाऊंगा, मतलब 6:30, हाँ ठीक है, 6:30 वाले में, मतलब 6:15, 6:30 वाले उसमें आ जाऊंगा मैं, ठीक है। हाँ 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 ठीक है, 6:15 तो मैं आ जाऊंगा, ठीक है। हाँ हाँ ओके। Okay, sorry for the interruption. So what I was telling is that, see, this conversion from a 2D system, from a 3D, system where we saw that there were actual 3D variables into, a 2D system is not, so you can't just naively do this, do this conversion. Okay, for that to be, true, or for that to hold good, it should satisfy what we call it as the squares theorem. Okay, so what we'll do is we will formally introduce the squares theorem in order to do this conversion. Okay, so the next step maybe, so what will be this step? This will be step 5, right? Okay, so the step 5 is, apply squares theorem. Okay, now in order to apply squares theorem, we must first know what is squares theorem. Okay, so squares theorem says, so this theorem says that for inviscid flows, but remember this theorem can also be applied for, viscous flows as well. Okay, so that's what I'm writing. So it can also be extended, it can also be extended for viscous flows as well. Okay, because in order to derive the Orr-Sommerfeld equation, you need to apply squares theorem, and there, the flow is viscous in nature. Okay, so remember this. So it says that for inviscid flows, or it can be extended for viscous flows as well, but the nature should be that, that are, so for inviscid flows, this is within bracket, that are parallel or nearly parallel. Okay, this condition also needs to be satisfied. So it can be parallel because the analysis that we are doing, this is, so the base flow is parallel, or at max it should be nearly parallel in nature. Okay, 2D, so it says that, so then the theorem says that 2D disturbances are stronger than their 3D counterparts. Okay, but the condition is provided the wave numbers are same. This is important. Okay, what it means is that in my 3D problem, let's say I have a wave number alpha 3D and I have a wave number beta 3D, then the effective wave number in 2D would be alpha 2D. Okay, now for the squares theorem, what we'll say is that the magnitude of alpha 3D and beta 3D, which is nothing but square root of alpha 3D square plus beta 3D square, this, this has to be equal to alpha 2D. If that is the case, then, you can argue that, you can apply something known as the squares theorem. Okay, so what this means is, as I was telling, alpha 2D, which is the wave number for the 2D case, should be equal to square root of alpha 3D square plus beta 3D squared. Okay, so I will just give you an idea. So I believe I mean, from the argument that I put forward, this is the argument behind the squares theorem, and that the wave numbers are same. But I'll just give you a small example. How do we compare this wave number for the case of, a 3D problem to an effective 2D problem. So remember, when we are doing the normal mode analysis, if we so the term in the exponent, we kind of wrote it as e power minus alpha ct, if you remember, plus alpha x plus beta y. That's precisely how we wrote the term in the exponent. Okay, now what I can do is I can write this as e power minus alpha ct. That's fine. Okay, there is an I here, remember. Okay, it is I alpha x plus I beta y. Okay, So this e power minus alpha ct plus I can write it as I times alpha x plus beta y. Okay. I hope this is fine. And what I can now do is, if I concentrate on this term, which is alpha x plus beta y, I can write it as, so this is important, okay, try to understand. So this term alpha x plus beta y, I can then write this term as alpha ex hat plus beta ey hat, and then I'm doing a dot product with a position vector which is x ex plus y ey. Okay, and that precisely is what this term that we write in this parenthesis. And then I can write this as some vector, we'll call it as lambda dot, let's say x test. So this lambda, this vector that you wrote, this lambda, this is known as a wave number vector. Okay, and in squares theorem what we say is that if I have a wave number vector in 3D, if I have a wave number vector in 3D, its magnitude should be equivalent, should be exactly equal to the corresponding wave number vector in 2D. Now the wave number vector in 2D, so what would be the corresponding wave number vector in 2D? It would just be, so this wave number vector in 2D, this lambda 2D, this is just going to be some, okay, I can write this as some alpha 2D times ex. Because in 2D, either you can have the y direction, and in this case, we can only have the z, we can only have the x direction. You need to discard any one of the directions basically. You cannot discard z because your flow itself is varying along z, and you cannot discard x here because the base flow is in the x direction, which means the only direction which you can discard without sacrificing the physics of the problem is the y direction. Okay, and that's why in lambda 2D I can have a wave number which is alpha 2D times ex and not alpha 2D times ey. Okay, this is important to realize. And then the magnitude of lambda 3D, which is the wave number in 3D, is nothing but square root of alpha square plus beta square, and this exactly has to be equal to the magnitude of alpha 2D, which is nothing but square root of alpha 2D whole square, and this just comes out to be equal to alpha 2D. And this condition, this is a very, very important condition, and this condition needs to be satisfied if you are applying squares theorem. Okay, so this condition needs to be satisfied for squares theorem to be true. Okay, okay, I believe you are with me so far on this analysis. Okay, all right, then what we do is, okay, we just said that we will not consider a 3D problem, we will consider an effective 2D problem where the wave number is alpha 2D. That's it, which means I can then rewrite my governing equations in in terms of a 2D problem. So the 2D problem then becomes, the 2D problem becomes, okay, so what does it become? So the continuity equation, remember, so let's write the continuity equation first. Okay, so if you remember the continuity equation in terms of the perturbed quantities, of course, because that's the variables that we're interested to find. It was u prime del u prime by del x plus del v prime by del y plus del w prime by del z equal to 0. But now I know that my problem is a 2D, which means I can simply discard this y term. I will simply discard this y term. Okay, I repeat, I cannot discard this term because the flow is in the x direction. I cannot disturb this term because the base flow has variations along z. Okay, which means the only term that I can discard without sacrificing the physics of the problem and by using squares theorem is that this y direction. Okay, which means the continuity equation then boils down to del u prime by del x plus del w prime by del z equal to 0. Okay, but remember, we also need to use the normal mode analysis, right? For example, in 3D, the normal modes were, u prime is equal to u hat of x times e power minus I alpha ct plus I alpha x plus I beta y. That was my normal mode. But now I know that this mode is not there. This wave number is not there because it's a 2D problem, and this alpha now just becomes alpha 2D, and this is very very important. Okay, see, initially when we were writing the normal mode analysis using in the 3D problem, we had alphas and betas, and these alphas and betas were the wave numbers in the 3D problem. Now I'm saying that I'm reducing this to a 2D problem where I'm discarding the y direction. But then you also need to be careful because this wave number in x now becomes, it is not alpha 3D, but now it becomes alpha 2D. Okay, so this then becomes, so this u hat u dash, which now will be function of x, it will be function of z, and it will be function of t, but it will not be a function of, I hope you realize that it will not be a function of y. And this is z, I'm sorry for that, this is z. And I hope you understand why now this u dash is a function of x, z and t. Okay, now because we are effectively now solving a 2D problem using squares theorem. So then this becomes u hat of z times e power minus I alpha ct plus I alpha 2d, okay, of x. And it's very, painful to write everywhere alpha 2d. So what we'll do is we will just, represent alpha 2d as, just alpha, some other variable alpha. But remember, this alpha is not the alpha that we wrote for a 3D problem. This is alpha corresponding to the case when we have a 2D problem. Okay, which means u dash of x, z and t is u hat of z. I can simplify this and I can write it as e power, and if I take, I alpha common, this precisely becomes x minus ct. Okay, that's it. That's the normal mode. That's the normal mode, okay, in the 2D problem. Similarly, you can show that your v prime is also a function of x, z and t, but remember, I don't need v prime now because I am basically solving a 3D problem. So I don't need this v prime variable. All I require is the w prime variable, which is the velocity component in the z direction. This will now be a function of x, z and t. Okay, and this is w hat of z times e power I alpha x minus ct. Okay, and similarly, I have p dash of z comma t as p hat of z times e power I alpha x minus ct. Okay, and maybe I will name this equation. So this continuity equation in 2D, maybe I'll name it as what? I don't know. Let's see. Okay, this is 10D, so maybe I'll name it as some 10A. Okay, and then this normal modes in 2D, I'll name it as, let's say, 10B, 10C, and 10D. Okay, so all that I need to now do is substitute these 2D modes, these 2D normal modes into the governing equations of the 2D problem. Okay, so the continuity equation, so I'll not now show the substitution. This you can do at your end readily. It's just substituting these normal modes into the governing equations for the 2D problem. So the continuity equation then looks something like this. Your continuity equation will turn out to be I times u hat of z, okay, times alpha plus dw hat by dz equal to 0. That's the continuity equation. Maybe I'll name this as equation 11a. Okay, the x momentum equation for the 2D problem becomes I alpha u minus c times u hat of z, okay, plus w hat times du by dz equal to minus I alpha p hat. Okay, that's your x momentum, and your z momentum becomes I alpha u minus c times w hat of z equal to minus dp hat by dz. Okay, that is your z momentum equation. See, now we have reduced the number of variables. The number of variables are now u hats, w hat, p hat, and alpha. That's it. It's just four variables. And in principle also we have four equations. It's an eigenvalue problem that we'll solve. That means the four variables are solvable in nature. Okay. Okay. All right. So we are almost there in deriving the famous, Rayleigh stability equation. But we have an important concept to understand now. Okay. Maybe I'll stop here for a couple of minutes. Uh, if if you have any questions to ask or suggestions, you can let me know. Okay, so I hope you understand the principle that why did we convert this to a 2D problem. As I was telling, in the 3D problem, we had like the unknowns U had, V had, W had, okay, and P had, along with alpha and beta. Those are also unknowns, okay. So there were a lot of unknowns, but we just had four equations, which means, in order to analytically solve this problem, we actually converted them into a 2D problem. Another benefit of, and the actual benefit of 2D problem is that, see, I can now use something known as the stream function. Okay, because we saw that for 2D and 2D axisymmetric problems, we can use the stream function approach. So then what I will do is I can now use a perturbed value of the stream function because the variables are solved for the perturbed variable, which means I can define now a perturbed stream function, which is, let's say, psi prime, and I can call this psi prime in normal mode analysis as, using normal mode analysis as some phi of z times e power I alpha times x minus ct. Okay, then you can ask me that, okay, what is the physical significance of this perturbed stream function? See, if I have a base flow, I can also define a base stream function. So let's say the base stream function looks something like this. This is my base stream function. Okay, let's say psi base. Then the perturbed stream function is that if I add perturbations to the flow, there will be perturbations in the velocity field. Equivalently, these perturbations will also be reflected in the stream function, which governs, the velocity field u, v, and w, or u and w in case of the 2D problem. Okay, which means the perturbations in the problem will actually give rise to a perturbed stream function, which gets perturbed from its natural state or the base state. And this perturbed stream function, let's say, would look, something like this. So this is the variation of the perturbed stream function with respect to the base stream function. And let's say this perturbed stream function is psi prime, and I hope you can understand that this psi prime is a function of x, it's a function of z, it's a function of p, just like the you know, other perturbed variable. And then I can write psi prime, this perturbed stream function, using normal modes as something like this. Okay, so this is like writing psi prime using normal modes. Okay. No. The point of using again stream function is that I can now correlate between the perturbed velocity fields and this stream function. For example, I can now say that u prime, which is my perturbed velocity field in the x direction for the 2D problem, this is equal to del psi prime by del z. But I know that u prime is what? It is u hat of z times e power I alpha into x minus ct. Okay, and what is del psi prime by del z? Del psi prime by del z is just d phi by dz of this quantity basically, which means this becomes d phi by dz e power I alpha x minus ct. Okay, I hope this thing is clear, which means I can simply now cancel this term, and then I can correlate, or I can relate, in fact, u hat of z is equal to d phi by dz. That's one relation. Okay. And maybe I'll name this as what, 12 or 13a. Okay. Similarly, for the other variable, I know that v prime is equal to minus, sorry, it should not be v prime, it should be w, because it's a 2D problem now. So w prime is equal to minus del psi prime by del x, right? Okay, Because see, the independent variables are now x and z, and the corresponding velocity fields are u and w, and I have defined stream function corresponding to this u and w. Okay, and then I know that what is w prime. W prime is some w hat of z, again e power I alpha times x minus ct. Okay, and let's evaluate this. So this is del x of phi of z times e power I alpha x minus ct. Okay, so this becomes, so what does it become? This becomes w hat of z equal to e power I alpha x minus ct, and this is equal to, so this becomes minus I alpha phi of z. Okay, times, of course this term will be there, e power I alpha x minus ct. Okay, which means I can then strike off this term, and then this becomes, or then I can relate w hat of z with this phi of z as, this is minus I alpha phi of z. Okay, okay, that's it. This means we have found out a relation between u hat of z and w hat of z in terms of phi of z, which is the eigenfunction for the corresponding, disturbance in string function. Okay, or maybe I'll call this as, let's say, 13b. Okay, let's do one quick check. Let's substitute this into the continuity equation. Let's, because we know u hat and w hat in terms of phi, let's substitute and check in the continuity equation. Okay, so if we substitute this in the continuity, so what was the continuity equation? It was I alpha u hat plus d of w hat by dz. Okay, and then if I substitute, what is u hat? U hat is just d phi by dz, so it is I alpha d phi by dz plus w hat is minus I alpha d phi, so this term becomes minus I alpha d phi by dz. Okay, see, it's exactly equal to 0, which means we know that, see, we have learned that if we define stream function, the, the continuity equation is trivially satisfied, and this is the same, this is the case, right? You can see that just by defining stream function and the part of stream function in the normal modes as well, the continuity equation is, trivially satisfied. So then I believe our final bit of the puzzle, this long puzzle which we had been doing since 2 classes, the final bit is then is to, write u hat and w hat in terms of phi hat, and then get a single expression for phi hat. You know, that's the ultimate problem, because if I can get a single expression for phi hat, I can then solve for phi hat and the corresponding eigenvalue. And if I know phi hat, I know the stream function. And if I know the stream function, I know the velocity perturbations as well. Okay, so that's the idea. So the next step and the last step of this puzzle is, maybe, okay, what is this step? So this is I don't know. Okay, let's see the step number. Okay, step 6. Okay, so the step 6 is obtain a single equation for phi of z. That's it. That's the ultimate step that you need to do. And for that, we will be taking help of the x and y momentum, x and z momentum equation of our problem. Okay. Again, I stop here for a couple of minutes. If you have any questions or suggestions, uh, you can let me know. Okay, I believe you understand the objective that we now need to derive a single expression for phi object by using the x and z momentum equation. And let's see how can we do it. So for example, if we pick the x momentum equation, remember we had the x momentum equation like I alpha times u minus c, okay, times u hat, that is fine, plus d of capital U by dz. Remember this capital U is the base flow, okay, this is something that we know already. D of u hat by dz times w hat is basically equal to minus I alpha p hat. Okay, and then I can replace, see, I know what is u hat and w hat in terms of phi, right? So u hat is just, d phi by dz, w hat is minus I alpha phi. So let's replace this and see. So it is I alpha times u minus c, u hat is minus I alpha phi, which means this becomes minus I square alpha squared phi. Okay, and this term w hat, so w hat is what? W hat is, sorry, I think I did a mistake. Okay, sorry, very sorry. So u hat is not minus I alpha phi, this is w hat. Okay, so u hat is what? U hat is d phi by dz, right? So this would be I alpha times u minus c, u hat is d phi by dz, and then it is minus I alpha d of u by dz times d phi by dz, and then this is equal to minus I alpha times p hat. Okay. Okay. So what I can now do is I can, cancel I alpha because it's everywhere. So it's I alpha, and I alpha. And then this equation becomes u minus c times d phi by dz, and this is equal to minus du by dz times d phi by dz equal to minus of p hat. Okay, and similarly if I write the z momentum equation, my z momentum equation was I alpha times u minus c of w hat is equal to minus p hat, and I can replace w hat as minus I alpha phi, which means it becomes, these terms become minus I squared alpha squared, okay, u minus c times phi of z is equal to minus p hat. Okay, and then I know that I square is equal to minus 1, which means this becomes alpha squared u minus c times phi is equal to minus p hat. Okay, maybe I'll name some equations. Uh, okay, this is 13. Okay, maybe I'll name this as equation 14a. Okay, and maybe I'll name this as equation 14b. Okay, see, now still there is a problem. Our objective is to get an equation for phi. Okay, we got two equations, involving phi from the x and z momentum, but there is this pressure. So somehow, in order to get a single equation for phi, which we are looking at, we somehow need to eliminate pressure, right? That's exactly what we need to do. So from this equation, what we'll do is we will just subtract one from another, and that's the simplistic way that is possible to get a equation for, to get a single equation for, for phi, basically the string function. So that's all that we need to do. But I'll stop here for a couple of minutes. I'll come back by filling my mug with some water. You can recap or do a quick recap of whatever steps that we had followed uh, in this analysis. Okay, so that's the final, bit of puzzle that we require to solve. Okay, so what we'll do is now as I said, our objective is to derive an equation for phi. Okay, so what we'll do is we'll just eliminate this p hat. So for that, what we'll do is we'll just subtract this equation from this equation. And if we do that, let's see what do we get. So we'll subtract 14a from, I mean, subtract 14b from 14a, and let's see what do we get. So we get u minus c, okay, times d phi by dz, okay, minus du by dz times d phi by dz, okay, and then I have minus alpha squared u minus c times phi is equal to 0, because p hats will basically cancel, which means I think I did some mistake. Did I do any mistake here? This is this, okay. This is fine. This is x momentum, and this is z momentum. Okay, I don't know. Did I do any mistake here? Oh, I think I did a mistake. See, um, I think I did a mistake. Yes, see, this term is minus dp by dz, right? Which means this term that I have written here, this is p prime actually. Yes, this is p prime, or you can simply write it as minus dp hat by dz. Okay, so this is minus p hat by dz, and this is dp hat by dz, which means if I want to now eliminate p, I need to differentiate first this term with respect to z, and then subtract this term, because in this term we have dp by dz. So what we need to do actually is we first need to take the derivative ddz of equation 14a, and then subtract this bit, subtract 14b from it. Okay, so let's do it. So let's take the derivative of 14a. So ddz, we are taking ddz of this equation. So ddz of what? U minus c, okay, times d phi dz, and then I have minus du by dz times d phi dz, and you also need to take the derivative. Okay, I hope I'm doing the algebra correctly. Let's check. Hmm, Good lord. I think I'm making one more mistake here. Let's see. Yes, I think I made one more mistake. So see, this W hat of Z is I alpha phi, right? So this is, when I substitute W hat of Z, this is just phi and not d phi dz. Okay, so this is just phi. So just phi of Z. Okay, I'm very sorry for these mistakes. Just not careful. So this is phi, and then this is phi. Okay, then this is fine. This is your Z. Okay, then this becomes phi, and then okay. Now let's take the derivative. I hope everything is in order now. So if I take a ddz, what does it become? So it becomes, okay. So differentiation of the first function, it becomes d of u by dz times d phi dz plus u minus c times phi double prime, where phi double prime is d2 phi by dz square. Okay, and then if I take the derivative here, this becomes minus u double prime phi minus u prime phi prime. I think that's it. Where this phi double prime is d2 phi by dz2, u double prime is d2 capital U, which is the base flow times dz, and single derivative are just the single derivative with respect to z. But see, what is this term? This is also u prime phi prime, right? And then I have plus u minus c phi double prime, okay, minus u double prime phi minus u prime phi prime. And also I need to take, also there is this pressure, and that would in any way get cancelled, so that's not a big deal. Okay, and which also means that I have this getting cancelled, and this becomes u minus c times phi double prime minus u prime phi. That's the derivative. And now if I subtract this term u minus c times phi double prime, okay, remember there is a pressure here. Okay, I believe you understand that. So there is a pressure because this term is minus. I'm basically doing this, so it is it would be, I think, minus p hat prime dp hat by dz minus p hat prime, and this p hat prime would get cancelled from the other term. So this is minus p hat prime, and this is minus p hat prime. And when I subtract this in from 4, I mean this bit minus 14b, this p hat prime would basically get cancelled with dp hat by dz from 14b. Okay, which means I have u minus c u double prime minus u double prime phi. Okay, then I need to subtract this term. I need to subtract this term, which is this. Okay, and this is minus alpha squared u minus c times phi, and this is equal to 0. Okay, and I think we are just there. Okay, so what I'll now do is I will maybe take u minus c common, so this becomes u minus c, and then this term is phi double prime minus alpha squared phi. Okay, and then I have minus u double prime phi, and then this is equal to 0, and this is what is known as the infamous Rayleigh stability equation. See, this is the equation. Okay, first of all, this is known as the Rayleigh, and it is named after Lord Rayleigh, who is very popular among fluid dynamists. So this is the Rayleigh stability. Actually, Lord Rayleigh has done tremendous work in stabilities. For example, there is something known as Rayleigh-Plateau instability. There is something known as Rayleigh-Taylor instability. Right. So it was a work done between Lord Rayleigh and G.I. Taylor. So you cannot imagine fluid mechanics or fluid dynamics in principle without the greats like Lord Rayleigh, G.I. Taylor, and Euler, and scientists like that. But anyway, so this is the infamous Rayleigh stability equation, and you can see that this is a single equation in phi, which means what? This means that I can just solve this equation in phi to get my Partoff string function. And if I know my Partoff string function, in principle, I can get using the relationship between velocity and string function, I can get the Partoff velocities basically. Okay, that is, I can get what is u hat of z. I hope you can understand that from phi, I can get u hat of z and w hat of z. Also, from phi, I can get psi prime, and from there, I can get u prime and v prime. Okay, you can get it from there also, like using the definition of normal modes. Okay, so the important bit is this is a single equation in phi from which we just need to solve this phi. Okay, and the more important, and it is more interesting that, see, although the Partoff quantities were they dependent on multiple independent variable, let's say x, z in case of 2D and time, we see that eventually the Rayleigh stability equation just reduces to a ODE, and in fact it's a second order ODE. Okay, so so the characteristics is that, so this the characteristics of Rayleigh stability equation is that, first of all, it's a ODE, which is second order, and more importantly, it's a homogeneous ODE. Why homogeneous ODE? Because I know that u equal to 0, small u equal to 0, or in fact phi equal to 0 here satisfies the system trivially. Okay, for example, if I put phi equal to 0, this term is 0, this term is 0, this term is also 0, which means left hand side equal to right hand side. This means that there exists a trivial solution, but we are not looking into trivial solutions. We are looking into specific solutions of phi, where which predicts whether the disturbances grow or decay with time, which means that this system, that equation, or I don't know what should be this equation number. It is 13, right? So this would be 14 is 14, and this is 15. So equation 15 that we have written, this is an eigenvalue problem. So homogeneous, governing equation, and we will see that the boundary conditions are also homogeneous. Okay, which means it's a typical, eigenvalue problem. So the eigenvalue that we are trying to solve for is C, remember, and the corresponding eigenfunction is phi. So this is the corresponding, eigenvalue. This is the corresponding eigenvalue. C, remember, is the growth rate, and this eigenfunction, phi is basically the eigenfunction. In fact, we are not only looking C, we are looking Ci. Remember, because the sign of Ci actually tells you whether the perturbations grow with time or perturbations decay with time. So it's the imaginary part of the eigenvalue which tells that if whether the disturbance, whether the perturbations basically grow with time or decay with time. Okay. Now let's quickly look into the boundary conditions, because I said that the boundary conditions should also be homogeneous in case of an eigenvalue problem. So let's have a look at this. So boundary conditions are rather simple. I know that at z equal to 0 and 1, that is at the top and bottom half of the channel, I know that the velocity should be 0 owing to the no slip. Okay, which means that my w prime, that is the z direction. Sorry, this is not the no slip. I'm very sorry. I'm very sorry. This is not the no slip. This is the no penetration. The no slip boundary condition will not work here because it's an inviscid flow. Okay, the only boundary condition is that there is no penetration of the fluid through the channels basically. Okay, so w prime, that's why the z component of velocity is basically 0 at z equal to 0 and 1, and this is 0 owing to the no penetration condition. But I know that w prime is what? It is w hat of z times e power I alpha x minus ct. But I know that this term cannot be 0 at z equal to 0 and 1. Okay, which means that my w hat of z at z equal to 0 and 1, this is equal to 0. Okay, and I know that w hat is equal to minus I alpha phi, which means the boundary condition is that phi at z equal to 0, this is 0, and phi at z equal to 1 is 0. That's it. Two boundary conditions, and it's a second order equation. Okay. Indeed, you can see that the boundary conditions are also homogeneous. So the boundary conditions, which are the no penetration conditions at z equal to 0 and 1. So the boundary conditions are also homogeneous, which means it's an eigenvalue problem that we are actually solving for. So the governing equation, this, subject to these two boundary conditions, maybe I'll write them as 16a and b. So the governing equation, which is this, subject to these two boundary conditions, okay, indicates that it's an eigenvalue problem, and we are solving for the corresponding c and phi, which is the eigenvalue and eigenfunction pair. Okay, so I'll write it down. So this means that this is an eigenvalue problem. Okay. And where phi of z is basically the eigenfunction and c is my corresponding eigenvalue. That's it. That's all that we require in order to know about the stability. And in principle, once c is known, I can always extract, I can always, write c as cr plus I ci. And, is this ci, it is the sign of ci. It can be like ci greater than 0. It can be ci equal to 0. It can also be ci less than 0. And if this is the case, okay, if ci is greater than 0, this is something that we have seen, right? So if ci is greater than 0, it's instability. If ci is less than 0, it's a stable system. Yes. Okay. Okay, so this ends. So by the way, you can see that in your Over-Sommerfeld equation, if you put Reynolds number to be equal to 0, you will exactly get this Rayleigh stability equation. You can do that check at your end because this is something that we have derived in the lecture series. If you put Reynolds number to be equal to 0, you'll basically get this Rayleigh stability equation. So Rayleigh stability equation in principle is a special case of Over-Sommerfeld equation when the fluid is inviscid, or in principle when Reynolds number is equal to 0. Okay, so let's do a quick recap because it was a long problem. Let's do a quick recap from beginning, like what did we do in this problem. Uh, we spend a lot of time here, but I believe it is worth it because the maths and the physics of this of these kind of analysis are really rich. Okay. So the question that we pose is that can we look into the stability of a given base flow where the base profiles are given to us, for instance the base velocity and the base pressure. We were asked, the question is that if I add certain perturbations, what happens to this perturbation? In principle, can we solve for actually these perturbations? So for that we say that okay, our objective then would be to write equations for perturbations, but in order to write equations for perturbations, I must first define the total variable, which I can write it as the base variable plus the perturbations. And in this case I assume that the fluid is inviscid and incompressible and base flow properties are known, from which what I did is I started off by writing a governing equation for a total variable, okay, in dimensional form. Then what we did is we have non-dimensionalized it, okay, using the characteristic scales to get the governing equations for the total variables in non-dimensional form. Then what I did is I wrote the total variable as the base variable plus the perturbations, where everything about the base variable is known. We saw that the base variable trivially satisfies the continuity equation, the base variable trivially satisfied the Euler equation, and in fact we saw that the base pressure is constant when you solve for the base variable, when you solve for the pressure using the given base flow, okay, in case of inviscid fluid. Okay, now once that is known, what I did is in order to get equations for the perturbations, I considered the total equation, subtracted the equations of the base variable to get the equations for the perturbations. Now once they are known, I do something which is known as normal mode analysis. Sorry, I do something which is known as linear stability analysis. It is known as LSA. The linear stability analysis says that in the equation of my perturbations, the nonlinear terms like v prime, grad v prime, these terms can be neglected. When this is true, when the magnitude of v prime is very very less than magnitude of the base variable, okay, under this circumstances you can neglect the nonlinear terms, and then it falls under the regime of linear stability analysis. Then what we did is a very important bit, okay, we wrote the linear set of equations in their component form, and we look into a very important bit which is known as the normal mode analysis. Okay, the normal mode analysis tells that using the concept of Fourier transform and inverse Fourier transform also, you can write normal modes in terms of something like this, which is a function in z times e power sigma t plus I kx plus ly. Okay, then what we said is we inserted these normal modes into the governing equations to derive equations for the functional forms of, let's say, u hat of z, w hat of z, and v hat of z. But doing so, we encountered a setback. The setback is that we saw that there are a lot of variables with lot of wave numbers, but the number of equations remains few. For which we applied something which is called as the squares theorem, which says that the 2D disturbances are stronger than 3D disturbances, provided their wave numbers are the same. Which means that the magnitude of the wave number vector in 3D, which is equal to square root of alpha square plus beta square, should be equal to alpha 2D. If that is the scenario, I can then apply squares theorem in order to neglect the problem in one of the spatial direction, which came out to be y in this physical problem. Okay. Now doing that, it enables us to derive equations in the 2D space, for example the x, z and x, z and a continuity equation by using squares theorem. And then what we do is we also wrote the normal modes in 2D form. Now when we substituted these normal modes in 2D form, we saw that the two velocity functions u hat and w hat, they can be reduced, or the problem can be recasted into a problem involving the stream function, because it's a 2D problem. And this means that we just need to solve for one variable, that was the stream function, for which what we did is we defined the stream function using a base stream function plus a perturbation, where the perturbed stream function can be written in terms of the normal mode. Okay. After that, we converted, or we correlated the velocity, the functions of velocity into the into the functional form of phi, and then solve for phi. Now in order to solve for phi, it appears that pressure was also in our problem, so we also need to eliminate pressure. Now when we eliminated pressure, we got a single equation in phi, which we call it as the Rayleigh stability equation, and this explains the stability of inviscid parallel flows. Okay. Now in the next class, what we'll do is, this is going to be the last class, and most probably tomorrow is going to be the next class. You will be a priori notified about that in emails, and also in the course website as well. So if there happens to be a next class tomorrow, what we'll do is, we will study that how do we apply this Rayleigh stability equation into predicting the stability of some simple flows. Okay. So we'll look into something known as the Rayleigh inflection point criteria. There's also something known as the Jortov's criterion and Howard semicircle theorem. We will look into these three aspects, because these three aspects actually show us how to apply the Rayleigh stability equation in order to predict whether a given base flow, if added perturbations, is stable or unstable. Okay. That's something that we'll do in the next class. Hopefully the next class is going to be tomorrow, that is on 12th April. I think it is from 4. But yeah, so if hopefully if there's and of course the next class is going to be the last class, and we will discuss this. And then what we'll do is, we'll do a quick recap of whatever we have learned, starting from the Reynolds transport theorem to ending the course at stability analysis. Okay. Okay, all right. So we'll meet maybe mostly tomorrow, and we'll discuss these things and do a quick recap of the course. Okay. Thank you very much, guys.